Hello, guys. So today we are going to talk about exponential and logarithmic functions and the relationship between the exponential and logarithmic functions. So let's get started. In the previous class, we have already learned what polynomial functions are and what kind of formats, what kind of structures they have. They have the structures of like x squared, x squared plus 5x squared plus 5x or plus 3, etc. And exponential functions have the structure a to the x, b to the x, 2 to the x, 3 to the x, or 5 to the x, etc. You can see examples here. For example, you have 2 to the x, 3 to the x functions, and there is an important difference between the polynomial and exponential functions. In the polynomial functions, you have x being in the base of the function, the varying part being in the base of the function, and in the exponential parts you have constants. But in the exponential functions, it is the reverse. In the base, you have the constant parts like 2 to the x, 3 to the x, 5 to the x. In the base part, you have 2, 3, 5, and in the exponential part, you have the varying part. You have x squared or x squared plus 3x, etc. And in the right side also, you can see the graphics of those functions. We have, for example, blue function, which is the x square function, polynomial function, and we have the red one, which is the 2 to the x function. After some point, the exponential functions start to grow quicker compared to the polynomial functions. For example, in this example, we have this point. After this point, after that intersection, it starts growing quicker compared to the x square function. The values are being greater than the polynomial values. Let's go to the third slide. So we have already talked about what a to the x and what exponential functions means, but we have some kind of restrictions on this a to the x functions. A cannot be 1 or a cannot be smaller than 0. Why a cannot be 1? If it was 1, if it were to be 1, then it would be just standard constant function for each values of x. It will produce 1. It will be a constant function, but we don't want that. We want our function to grow or to decay according to the a values. So that's why it cannot be 1. Why it cannot be smaller than 0? Assume that it is smaller than 0. For example, in the case of minus 3, fx equals minus 3 to the x, and if x is 1 over 2, for example, minus 3 to the 1 over 2, which is the square root of minus 3, which becomes like a not real number, but a complex number. We don't want complex numbers in this case, so that's why it cannot be smaller than 0. And domain of the exponential function starting from minus infinity to plus infinity, we can give any kind of number that we want. There's no restriction here. Why there is no restriction? We don't have any kind of denomination, so that the denominator makes it 0. We don't have the denomination problem. We don't have square root problem, which is the square root of function cannot be negative. We don't have that kind of thing here also. And this is not a logarithm function, so we don't have any restriction in the domain, so it can take any real number value. For the range one, since this a is the positive number, anything multiplied by itself positively, any positive number, it will produce a positive number. That's why it will be greater than 0, and it will go up to infinity. So the slide also mentions about the horizontal and vertical asymptote. It is not very important for now because we will be learning horizontal asymptote and vertical asymptote when it comes to limits. But here, for example, when it goes to the plus minus infinity, when x goes to the minus infinity, the function itself, the value of function itself goes to 0. That's why it is called horizontal asymptote. So we have basic exponential rules such as a to the m, a to the m times a to the n equals the a to the m plus n, a to the m divided by a to the n equals a to the m minus n, a to the m to the n equals a to the mn, and a to the 0 being 1 and a to the minus n being 1 over a to the n. So here we have examples, but I would like to mention about, for example, for the third rule, assuming that we already know the first rule, a to the m times a to the n equals to a to the m plus n, we can prove this third one, because what we are doing here is we have two terms, and we are just summing the exponents of those two terms. We have how many terms we have in here? We have a to the m times a to the m times a to the m times a to the m. How many a to the m's we have? How many of those terms? And many a to the m's we have. So we have a to the m times a to the m, which is a to the 2m, and then 3m, then 4m, etc. How many m's we have? We have n many m's, so m plus m plus m. It is just m times n. This is the proof using the first formula in here. So we have base function, for example, we have 2 to the x function, but we can transform that function, and we can shift that function according to the values that we add or removed to the function. We can shift it to the right in the x-axis, to the left in the x-axis, or up on the y-axis, or down on the y-axis. If we 2 to the x, we already know the function 2 to the x, which is the blue function. For the for the second function, we are removing 3 from all the x values. So this is the second function. It is the orange function, and it makes the function move 3 to the right in the x-axis. To the right means it is in the x-axis. It makes function move right in this coordinate, xy coordinates. Why? Because in order to compensate this minus 3, we need to increase all the x's plus 3. So for example, we have 2 to the x. We have, assuming that our x is 2 and y becomes 4, we have two 4 point on this function, on this graph. And in order to get the same result for in the second function, we need to have 5 as the input for the second function, and our point 2 4 point for the first function becomes 5 4 point in the second function. So in order to compensate, in order to get the same result for the first and second function, we need to increase x by 3, and we are doing this for the all values in x in the blue graph. That's why it is shifting right by 3. If it were to be plus 3, then we would shift it to the left in the x-axis, to the negative side in the x-axis by 3. And for the third example, when we compare third example with the second one, we are just increasing all the y values by plus 1. We have already a y value here, and we are increasing all of them by plus 5. When you increase the y values by plus 5, you are just moving your graph to the north, to the up. If it was to be, if it was minus 5, we need to we are it means we are moving our graph to the negative side, negative y side. So for the growth and decay functions, we have growth functions. When a to the x, a being greater than 1, it is a growth function. When a is between 0 and 1, it is a decay function. uh, you can see from the graph, it is the blue function. It's the blue graph. It is the a being the 2 and 2 to the x. It is growing as x increases, y is also increasing, but y is also of course increasing and going to the infinity quicker than x. And When you give, for example, x is 0, it becomes 2 to 0, which is 1, and that's why it's intersected with 2, 0, 1 in this axis. And when it is negative, when x is negative, you have y equals 2 to the x, but x being the negative, so you can rewrite it as 1 over 2 to the x, and this time x is positive number. Then 1 over 2 to the x, then as x is getting smaller and smaller, the denominator is becoming greater and greater for the negative numbers, the denominator becoming greater and greater. So it is going to do infinitive as x goes to minus infinity. Assume that at x is minus infinity, it is becoming like 1 over 2 to, 2 to the minus infinity, 1 over 2 to the infinity, which denominator goes to infinity, 1 over 2 to infinity, it goes to 0. That's why it is going to 0. For the a being is between 0 and 1, it is standard decay function. And for example, 1 over 2 to the x, as x grows, the denominator starts growing 1 over 2 to the x, because of in the denominator you have 2 to the x, so it keeps growing and growing, and the y value is keeps becoming smaller and smaller. That's why 1 over 2 to x goes to 0 as x grows. For the minus x values, as x goes to the minus infinity or minus very very big number, 1 over 2 to the minus very big number, you can get rid of minus, and you can convert this 1 over 2 to the 2, and you will end up with 2 to the some very big number, which goes to infinity in this orange graph. We have special exponential function, which is a and a to the x, and a being the 2.71828. It is of course growing quicker compared to the 2 to the x, because 2 to the 7 1 is greater than 2, and it is a special function such that in the derivative functions we will learn, but when we take the derivative of e to the x, it will become e to the x again. It will be itself. So we have basic exponential problems here. 2 to the x, as we know, 32 is 2 to the 5, so x becomes 5. The 81 is 2 to the 3 to the 4, so x becomes 4. And in the third problem, we have 5 to the x equals 12. So we need to leave this x alone so that we can find what x is. We need to multiply, not multiply, but we need to take logarithm of both sides, or ln of both sides. In this case, it's taking ln of both sides. Since we didn't learn logarithm yet, I will be solving that problems later, but in this video. So what does logarithm mean? We have logarithm base 2 of 8, which is 3. The logarithm asks the question, for example, to which power should I raise this to so that it becomes 8? To which power should I make the exponent part of this 2 so that it becomes 8? We cannot make it 1 because it becomes 1. If we were to make it 2, it would become 4. So we need to make it 3. We need to make exponent part of 2 3 so that it becomes 8. This is the question that's answered by the logarithm. So a to the x equals y, and if you take the logarithm of the both sides, you will end up with logarithm of a to the x equals logarithm of base a of y. Logarithm of a base a of y, this is equals logarithm of base a to the x. So you have inside a to the x, and in outside you have logarithm a, and they will cancel each other, and then you will end up with x. I'll be talking about this later also in the logarithm rules. We have such rules. For example, 10 10 to the 2 equals 100, 3 to the 4 equals 81. So logarithm 10 to the 100, we can answer this by looking at the meaning of logarithm. To which power, to what power I should rise this 10 so that I can get 100. I should rise this 10 to the power of 2 so that I can get 100. I should rise this 3 to the power of 4 so that I can get 81. If I rise it to the power of 3, I can get 27. So it doesn't solve my question. So we can, since we have already learned the taking logarithms of the both sides, we can solve this question also. Problem 3, when you take the logarithm of the both sides, ln is just a logarithm with base being e, special number e, that we have learned in the previous slide. We have learned this number, special number. Ln means logarithm with base being e, logarithm function with base of it being e. So that's why when you take ln of both sides, we have ln 5 to the x equals ln 12. Ln 5 to the x, you can put that x to the side of the logarithm that we will learn in a couple of minutes, and you will end up with x ln 5 equals ln 12. And when you divide both sides with ln 5, you will end up with ln 12 over ln 5 being x. So we have learned logarithms and we have also learned exponentials. Now there's a special relationship between those. They are the inverse of each other. You have y equals a to the x, which is the exponential function, and you have y equals logarithm a to the x, which is the logarithm functions. They are inverses such that the domain of one becomes the range of one, and the range of one becomes the domain of another. For example, you have 3 y equals 3 to the x here, and when you give 1, 2, 3 for the x values, you will end up with 3, 9 and 27 for the y values. You in the domain you have 1, 2, 3, and in the range you will have 3, 9, 27. For here it is the reverse. Why? Because you have 3 here, logarithm y equals logarithm base 3 of x, and when you have, for example, 3 here, you will have 1. When you have 9 here inside, you will have 2, because it is answering the question of to which power I should raise this 3 so that I can get 9 inside. So I should raise 3 to the power of 2 so that I can get 9 at the inside. That's why you have 3, 9, 27, etc. in here in the x, and you have 1, 2, 3 being the exponential part of this a, which is the 3 in this example, being here. So y becomes 1, 2, 3, 4, etc., and x becomes 3, 9, 27, 81, etc. So uh, 3, 9, 27, 81 was the range here, but it becomes the domain here. And for this one, 1, 2, 3, 4, 5 was the domain in this function, and in this function it becomes the range, it becomes the y. That's why domain and range are reversed in the second condition, so they are the inverses of each other. And since they are the inverses of each other, when you take composition for those functions, we have also learned that in the previous lecture, when you take the composition of inverse functions, they will cancel each out, and you will end up with x. So you have a to the x, for example, logarithm a to the x. When you compose them, whether compose this one first with this one or this one first with this one doesn't matter, or doesn't matter, they will cancel each other. For example, here first, this function logarithm a to the x function is taking this function as an input parameter. So logarithm a to the x, instead of input parameter x, you have a to the x. So logarithm here outside, you have logarithm a function composed by inside you have exponential function, they will cancel out each other, you will have x. And in this one you will have a to the x, and in the power uh, as an argument, you are taking the second function as an argument. You have a to, instead of a to the x, now you have a to the logarithm a to the x, and this is also canceling each up because outside you have exponential, inside you have logarithm. They will cancel each out, and you will end up with x. And on the right side, you can see the 2 to the x and uh, logarithm base 2 of x functions. 2 to the x is the standard function that we know, which is the function with blue color, and 2 to the logarithm base 2 of x being the orange function. And since they are the inverse of each other, they are the reflection of each other also with regards to reflection, with regards to this x equals y axis. The inverse functions are the reflections of each other with regards to this y equals x axis. And you can see as x is increasing, the y values are also increasing, and but they are increasing decreasingly. So and x is the graph is crossing with the x-axis at this point. Why? Because when you give one as an input parameter, to you will ask the question, to which power should I raise this to so that I will get one? So which power of 2 is 1? Zero power of 2 is 1. So that's why it is crossing with this. And when you take when the x values goes closer and closer to zero, the y is going to minus infinity y, because when assume that x is zero, x cannot be zero, but assume that it is zero, to which power of 2 is goes to zero, minus infinity power of 2 goes to zero. That is why it is going to minus infinity as x is becoming closer and closer to zero. So you have ln x and logarithm e to the ln x being the logarithm base e of x. It is just a simpler form of saying logarithm base e to of x. So we have logarithm rules here. Ln x and e to the x are inverse of each other. So when you compose them, they will cancel each out, and you will end up with x in both cases. And you have logarithm a. Inside you have x times. If you have inside x times y, you can separate it as logarithm base a of x plus logarithm base a of y. If you have a division inside, you can subtract them. Logarithm base a of x minus logarithm base a of y. And if you have power here in the as an input inside, you can take those power and put to the side of the logarithm. Those are the logarithm rules. For example, you have ln x to the 5. You can just uh, take this power and put to the outside of the function 5 ln x. It is equal to 5 ln x. Or here in the case of logarithm 10, inside we have 1000. Well, this is like 110. Logarithm 10 to the 100. To which power should I raise 10 so that I can get 100? 2. To which power should I raise 10 so that I can get 10? 1. So 2 plus 1 equals 3. Okay, I could have said something like, instead of 100 times 10, 10 times 10 times 10, then it becomes 1 plus 1 plus 1 instead of 2 plus 1. And we have such some examples and solutions of those. We have already learned that logarithm to the 16, 16 we know to the power 4. So you can put 4 outside of the function. 4 times logarithm to the 2, logarithm to the 2 is 1, so you will end up with 4. You will have logarithm 3 inside 1 over 27, 1 over 27, 3 to the minus 3, 3 to the power minus 3. You can put minus 3 outside, and logarithm to 3 to 3 is 1. You will end up with minus 3 times 1, minus 3. Ln e to the 5 equals, you can again put 5 outside of the ln function, and 5 ln e, ln ln e, ln being the logarithm with base e, and inside you have e. Uh, it will be 1, and for 1 times 5 will be 5, and ln x equals 2. You need to convert this to exponential. In order to do that, you need to take the exponential of the both sides. If you take exponential of the both sides of this formula, e to, for example, since this is logarithm with base e, we need to use e as an exponential. So you have e to the ln x equals to e to the 2. E to the ln x, they will cancel each out because you have e in the base, you have e in the and in the exponential part you have a logarithm. So that logarithm and that exponential, they will cancel each out, and you will end up with x equals e to the 2. They will cancel each out, just like in the case of here, or or here. So that is the everything that I can explain about the logarithms and exponential functions. I hope you enjoyed this video. Thank you for listening, and until next time.